Welcome to Sequences. This video is going to be focused on finding different patterns. So a disclaimer here is this video is for you to watch after you've already explored different patterns and are still struggling with distinguishing between which formulas to use and look for in these certain situations and certain sequences. So it's very explicit here that I'm going through and talking about different patterns to explicitly look for. So the first one you definitely want to look for is a linear pattern. And of course, this would be an arithmetic sequence, right? So if you're looking for any kind of linear pattern, you want to check and see if A2 minus A1 is equal to A3 minus A2. You're just looking that the common difference would be the same. I know that you can obviously do this one in your head, but if you had fractions or something like that, you just want to double check. So here you can see the common difference is in fact 4. And so we can go ahead and use, I'm just going to use the generic A sub 1 formula here. If you need some more help with arithmetic formulas, you can go and watch my video that specifically goes with arithmetic sequences. So right here we have A sub 1 is 7, our difference is 4, and we have n minus 1. Great. Another pattern you want to look for is a quadratic pattern. And so you would start off looking for a linear pattern here. And so, okay, well, plus 3, plus 5. No, it's not linear, but I am noticing something interesting. So if this first line had worked, it would have been linear, but it's not. So not arithmetic. Let's check something else now. The second difference, ooh, look at that. I'm adding 2 each time for my second difference. If the second difference is constant, then this is some kind of quadratic pattern. And so what I like to do is go ahead and set up a little chart here. I love charts. And so n, 1, 2, 3, 4, 5, and then this is a sub n, so this is 3, 6, 11, 18, 27. Sometimes this just helps me figure out what the pattern is. I know that somewhere in here I'm going to have an n squared, right? So n squared is 1, so 1 squared, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. And then I try to ask myself, okay, well, how can I get the n squared to be the a sub n value? So a lot of you can see that very quickly on that, oh, for this one, oh, it looks like 1 to 3 is adding 2. Well, 4 to 6 is also just adding 2. So my formula, my explicit formula would just be an n squared plus 2. But again, it could be subtracting a value, it could be multiplying by something, so you just have to kind of play around with that and see what you're doing to that n squared. Another pattern to look for is a cubic pattern. So I'm going to go ahead and do the first difference. And our first difference is not constant, so it is not linear. So next thing, I'm going to do the second difference. Well, guess what? Our second difference is also not constant. So what I'm going to do now is my third difference. Oh, look at this one. Okay, so the third difference being constant means we have something that is cubic. So again, if I set up my nice little chart here, I can think, okay, 1, 2, 3, 4, I'm given 5 terms of 0, 7, 26, 63, 124. Again, some of you may see this right away if you know your cubics very well. If you don't know your cubics very well, then go through and actually write them out. So 1 cubed, 2 cubed, 3 cubed, 4 cubed, and 5 cubed. I think now it's easier to see what am I doing to n cubed to get my a sub n number. And you can see that I'm subtracting 1 from that value. So here, a nice explicit formula would just be n cubed minus 1. Great, let's look at some more. All right, let's go ahead and look for an exponential pattern. I'm going to start off by just, again, looking at my first difference. And my first difference is definitely not constant, so it's not linear. And I can try my second difference. And that one's also not constant. So again, you can keep going if you want to. But even when you keep going, you realize the third difference is not constant either. So it's not linear, it's not quadratic, it's not cubic. I really want to go towards something else now. So what I am noticing is that here, if I take 6 and I multiply by 3, I get 18, right? Okay, cool. And if I take 18 and multiply by 3, oh, I get 54. Ooh, and you can double check it. If I multiply by 3 again, I also get 162. Now, it's interesting that if you look at the second difference, you actually multiply by the same values. So 12 to 36 is still multiplying by 3. And then, of course, even 24 to 72 is still multiplying by 3. So somewhere in here, that means I have an exponential pattern where my B value / my R value is a 3. But obviously, this is not geometric because the problem is I am not multiplying by 3 as I go along here. So again, you know me, I love my charts here. Let's go through and look at our 5 terms. And what I mean by this R value, I hesitate to say R value. I more want to look at this as being some kind of exponential where maybe I even add on some kind of value or subtract something from it or whatnot. So we'll see here. So it's more like a B value. And so 4, 10, 28, 82, and 244. So I'm going to do 3 to the n because I know my base is 3. So 3 to the n, so 3 to the 1 is 3. 3 squared is 9. 3 to the third is 27. 3 to the fourth is 81. And 3 to the fifth is 243. Oh, now you're seeing it, right? Yeah. Because now, what am I doing to that value to get the a sub n? You can see I'm just adding 1. So right here, a sub n is just 3 to the n plus 1. But notice how even finding the first and second differences can help you find what that base value is that you're going to need for that 3 part, like the base of this exponential pattern. Ooh, one of my other favorite ones is looking for different factorials. Okay, so if you're not familiar with factorials, please make yourself familiar with them. So 1 factorial is just 1 because that's how many numbers there are to get to 1. 2 factorial is 2 times 1, so it is 2. 3 factorial is 3 times 2 times 1, which is 6. 4 factorial is 4 times 3 times 2 times 1, 24. If you've never seen a factorial, you can kind of see where this is going now, right? So you just take whatever factorial you're using and you multiply it by every number below it till you get to 1. So 5 times 4 times 3 times 2 times 1, which is 120. Oddly enough, though, 0 factorial is 1. Not that I need that in this situation. That's just my own kind of, imparting my wisdom to you here that 0 factorial is 1. So here, if I am looking for what I'm doing with these factorials, I have these lovely terms here. And if I'm looking at how they are related, yeah, some of you can already see it exactly. So if I have n factorial, 1, 2, 6, 24, and 120, you can see here that you are just adding 1 to them. So a sub n equals n factorial plus 1. So that is another pattern you can look for. Now right here, this is interesting. This is going positive, negative, positive, negative, positive. Okay, well, if I had some kind of geometric sequence, I could multiply by a negative and that would make it go back and forth and back and forth. But if you watched my video on geometric sequences, you know that these would have to be constant for the ratios. And negative 3 over 1 does not equal 5 over negative 3. So that would not work. So this is not geometric. So the R value does not exist. It's not a negative value. What I am noticing, though, that if I didn't have it be negative, I would have 1, 3, 5, 7, 9. And that to me looks like a very arithmetic pattern, right? Yeah, so something to play around with there, that I could write a formula for an arithmetic sequence and go up 2, right? So that's my common difference. So I have 1 plus 2 times n minus 1. Okay, well that would take care of the 1, 3, 5, 7, and 9 part. But then now what? Well, very interestingly enough, if you have a negative 1 to an even power, so an even power, you get a positive 1. If you have a negative 1 to an odd power, you have a negative 1. We are going to use this information. Okay, so our first term is positive, which means I need it to have an even power. Well, 1 is not an even number. So what if I take negative 1 and I put it to the n minus 1? Do you agree that now if I plug in the number 1, I get 0, and negative 1 to the 0 is positive 1? Great. What if I take that and multiply it by this other arithmetic pattern over here, the 1 plus 2 times n minus 1? So now this part over here takes care of the 1, 3, 5, 7, 9, going on, yada, yada, yada. Whereas this part here takes care of the positive, negative, positive, negative, positive, negative. Ooh, yeah, let's check and see if this works now. Okay, so let's go ahead and check our 5th term here. So if I was looking for a sub 5, I would have negative 1 to the 5 minus 1, and then I would have 1 plus 2 times 5 minus 1. Okay, so I have 2 times the 4 inside here. Give myself some more space. 1 plus 2 times 4. So that is 9. So that does take care of the 9. And we know negative 1 to the 4th is a positive 1. So that does equal 9. Yay! Okay. Now let's try one of the other numbers. Let's try the 4th one, see if we get negative 7. Okay, so let's try a sub 4. Negative 1 to the 4 minus 1, and then 1 plus 2 times, oops, that needs to be a 4 minus 1 inside. Okay, so now I have, negative 1 to the 3rd is going to be a negative 1. Whereas over here I have 1 plus, that's a 3, so 1 plus 2 times 3 is 6, and that gives me 7. And that indeed does give us that negative 7. So notice when you have these positive, negative going back and forth, this part right here can come into play. And so you may need to use something like this to go back and forth between positive, negative numbers. So that's a fun one. Ooh, another fun one. Okay, so right here, numerator, denominator patterns. This is where I'm just telling you, hey, let's go ahead and look at these separately, okay? So if I look over here and I look at my numerators, I have 1, 2, 3, 4. Let's use negative 2, 4, negative 8, and 16. Great. So here you can kind of see, oh, well, I'm just multiplying by negative 2. So it seems like a very geometric pattern, right? It's a geometric sequence, right? That's the R value. And so for my numerator, I can write my first value. And then here you go. We're going to use this formula. And so I have a sub 1 is negative 2. And then my R is also negative 2 in this case, and I have n minus 1. So that should take care of the numerator. Okay, well now let's look at the denominator. The denominator is more of a linear pattern. It's 5, 7, 9, 11. Great. So I'm going up 2 each time, so it's the arithmetic pattern, right? And again, we'll use, right there, a sub 1 plus d, and then n minus 1. So if I were to use 5 as my first term, I would have 5 plus, I'm adding 2 each time, and I would have n minus 1. So notice here how the numerator and denominator have different patterns, but all together, this would be my explicit formula. So Lots of different fun patterns that are not necessarily arithmetic or geometric, but maybe a mix of things, or like I said, factorial. So just to recap, if it's not standing out as being arithmetic or geometric right away, go ahead and look for, if it's not that linear, look for quadratic, look for cubic. Go ahead and look at those factorials, look at different exponential patterns, look and see if the numerator and denominator can be written as different types of patterns. Try a combination of all of them because there are endless possibilities. So have fun with it.